Enough to make snowmen.
Yeah.
Good. Let's see. So I'm starting the. Whoops. Oh, maybe it's here.
Can we post the slides in the chat, do you think?
Oh, heck yeah, right.
Oh, yeah. Right.
How do I do that?
Thank you for remembering. Yeah, apparently you can just put it in your Dropbox and then put the Dropbox address in the chat, and that works.
Okay, but this will work too, hopefully.
Okay.
If I can find the chat. So how do I make this big again? Let me just stop sharing screen a minute.
Okay. Right.
Where's the chat gone?
I think you have to click on the chat icon to make it come up.
Oh yeah, and I'm sorry, I'm doing the wrong thing. Of course, I shouldn't drag the thing. I should give you a link.
Right. Yeah. Just in the chat, paste the link. Right.
Okay, that should work.
There it is. All right. Very good. Thank you.
Right. Thanks.
So, Dominic, are you introducing Tom?
I believe so, although I don't think he needs much introduction.
No, that's right. At this point, that's true. Yeah.
Okay, shall I start?
Yes. Wait. First, let me mute everybody, and then you two unmute yourself.
Yeah.
Okay, I've unmuted everyone. Now go.
Okay, well, for our first lecture today, we have Tom Bridgeland's third lecture of his series. Thank you.
Okay, thank you. So let's just try and remember briefly what we did. So in the first lecture, we talked about the wall crossing formula in Donaldson-Thomas theory. And I talked a bit about Stokes data and iso-Stokes deformations in the theory of differential equations. And then I said that actually, these two things look the same, but with a different group. You have to replace GLN with this group of automorphisms of the torus, symplectomorphisms of the torus. And we said that the isomonodromy equations become some kind of, this Plavansky equation. And then in the second lecture, I basically discussed the geometry behind that equation and tried to give an example or a class of examples of these complex hyperKähler structures that you get that way. So in this lecture, I'm going to be talking about how do you get from the DT invariants to this complex hyperKähler structure. Okay, so, and then doing some examples. So the basic way you do that is by trying to solve some class of Riemann-Hilbert problems. So I'm going to introduce those now, and then most of the talk will be examples. Okay, so at the risk of sounding like a broken record, let's just look at this equation once more. Okay, so this was, again, I'm thinking, it's always my guide is to think about the finite dimensional case first. So think about GLN, and we thought about this differential equation. So remember, it had an irregular singularity at the origin, so it had a pole of order 2 there. And if you look at infinity, it actually has a regular singularity, so just a pole of order 1 at infinity. Okay. So I just want to remind you of this because what I'm going to be doing is very much inspired by the work of Gayato, Moore, and Knightsky, and it's very closely related to what they are doing. And I'm certainly happy for you to give them all the credit, but I don't want you to think I'm doing exactly the same as them, because that could be confusing. So I just want to say that what is the analogous thing to what they were doing? It's something slightly different. It's something that comes up in what's called TT star geometry. And it was studied by Chicotti and Vaffa. And here you have an equation like this one. So it looks just like ours, but it has an extra term here, which is related to this guy by some complex conjugate. Okay, so this connection has two irregular singularities, one at 0 and one at infinity. and they're somehow related by some complex conjugate, basically. Okay, so there is some different story about these things. You know, it's very closely related because, for example, near epsilon equals 0, you would still want to talk about Stokes data and so on. So it's very closely related, but it's not the same story, and you know, one should bear that in mind. Okay. So in this finite dimensional setting, this equation is what comes up in the theory of Frobenius manifolds. This equation is related to this subject of TT star geometry, which I know next to nothing about, I'm afraid. Okay, so that was that equation again. And let's just recall how we defined the Stokes data. So the crucial thing was that there exist canonical solutions to this equation in half planes. Okay, and these solutions are canonical because they have good asymptotics as epsilon goes to 0 in that half plane. So remember, we have these rays, which are called the Stokes rays, which are spanned by the differences of the eigenvalues of the leading order term of our connection, so U. So we look at the differences in the eigenvalues, that gives us a bunch of rays, you know, the span of those things gives us a bunch of rays in the complex plane. And if I take any other ray, a non-Stokes ray, then there is a well-defined solution to this equation, canonical solution, on that half plane. And so if I have one of these Stokes rays, I can just perturb it in both directions and compare the two solutions I get, and that will give me an element of my group G. Okay, and that's what this Stokes factor associated to that ray is. Okay, so now what we want to think about is, suppose someone gives you the matrix U, so we know what the leading order term is, and also tells you what the Stokes data is. How can I reconstruct the connection? Okay, because that's the situation we want to be in. In this DT theory world, in this high infinite dimensional world, the DT invariants are giving us the Stokes data of this connection. We know what the leading order term is, that's just this central charge. But what we don't know at all is that sort of second term, that V, or I was calling it F as well. That's the thing that really gives me my hyperKähler structure. Okay, so how do I do that? So that's where this Riemann-Hilbert problem comes in. So again, we're considering this finite dimensional case first. So exactly what I've just been saying, suppose we have the leading term and we have these Stokes factors. How do we get the connection? Well, what we actually do is we actually, more than just the connection, we actually try and get these canonical solutions. And then of course we can just differentiate them to get the connection. And that should be an epsilon. So what we do is we basically just try and construct these solutions. So they exist on these half planes. They have given asymptotics as epsilon goes to 0. We should expect them to grow moderately as epsilon goes to infinity because they're solutions to a connection with a regular singularity at infinity. And then we know how they jump. So we know how to compare solutions for different half planes. Okay, so this is saying that if I take some convex sector and I have two of these non-Stokes rays, then the relation between these things should be, this is the product of the Stokes factors for the rays in that sector. I mean, I did introduce that notation at some point, but it's a long time ago by now. Okay, so this last condition, I've written it in a rather fancy way. And the whole problem I've written in a slightly confusing way, possibly, because later I want to consider the situation where there are infinitely many rays. But if you prefer, you can think of a single function which is discontinuous. Okay, so imagine defining a single function where I define it to be equal to YR on the ray R. Okay, so what will happen then is you will have these asymptotics, but it will be discontinuous across the rays, and it will precisely jump by the Stokes factor as you move across the ray. Okay, so that's a good-looking problem because we basically have prescribed the jumps and the behavior at 0 and infinity. Okay. So, I mean, again, Gautam, Moore, and Knightsky would have seen a slightly different Riemann-Hilbert problem, because instead of this condition at infinity, they would have had another condition like this, and there was some reality, you know, what happens to the solution when you complex conjugate epsilon. Anyway, so this is the Riemann-Hilbert problem we want to think about. And I should just say that even in this finite dimensional setting, you know, existence and uniqueness of these solutions is not guaranteed, and, you know, is a difficult thing. So this is very much related to Hilbert's 21st problem, which asks for a differential equation with prescribed monodromy around points in the plane. So that would be a question about differential equations with regular singularities, but this is a rather similar thing. It's asking about a Riemann-Hilbert map, only except this is an irregular version. And, you know, those are subtle problems. Okay. So, right, so that's the kind of finite dimensional setting, and then we're just going to go to the sort of infinite dimensional DT setting now. So just remind you where we were with that. I mean, the starting data I always begin with is some Calabi-Yau3 triangulated category with a stability condition. That's the context where, I mean, it's a very general context where one can hope to define DT invariants. There is this lattice and this torus. And then we defined for each ray in C star, we defined some element of this group of symplectomorphisms or Poisson automorphisms of this torus by this, well, it was a time-on Hamiltonian flow of the DT generating function on that ray, and we rewrote it in this form. And then we had this, this wall-crossing formula, which, as I said, looked like some iso-Stokes condition. Okay, so again, now we're going to want to try to reconstruct, yeah, maybe I'll write this on the next slide. So the corresponding connection, which the DT invariants are supposed to be describing the Stokes data of, looks something like this. The leading term is this central charge of the stability condition. And then there is some mysterious thing here, which we know is some Hamiltonian vector field on this torus. But, you know, we don't know it. We just know it's, yeah, it's just defined implicitly by having the correct Stokes data. And so this is really what we're wanting to do. We're wanting to take the DT invariants, think of them as Stokes data, and try and get our hands on this function f, because this is what's going to define as the nice geometric structure on stab. Okay, and we said that if you repackage this function as a function on the tangent bundle to stab, then it satisfies this isomonodromy equation becomes this Plebanski equation, and that gives you the existence of some complex hyperKähler structure. Okay, so, right, so we've got to do the analogous thing in this infinite dimensional setting now. So it means we need to look at maps into this group of symplectomorphisms of the torus, and I'm a bit scared of that group. So what I do instead is I fix a point on my torus and evaluate all automorphisms on that point. Okay, that's a perfectly reasonable thing to do, because then I will be looking for maps into the torus. Okay, so, I mean, the thing I'm going to write down here should be entirely analogous to the one we had before. We just changed the group. But as I say, we're going to compose with the evaluation map from this group to the torus, which just evaluates some symplectomorphism at some point. Okay. So just to be clear, this Riemann-Hilbert problem now depends on two pieces of data. First, the stability condition, which you can really just think of as the central charge, because those are, you know, locally, that's the only data. And then also a point of this torus, which I'm going to write as psi, but, you know, it's also exp of some theta. And theta is living in the tangent space to stability conditions at that point. It's a map from gamma to C. And it's exactly the same theta we had in the previous talk. So remember, we had our coordinates on our hyperKähler manifold were somehow zi's, which were these central charge coordinates, and theta i's, which were coordinates on the fibers of the tangent bundle. And so that's that same theta. And then we just do the same thing. So we look for maps from appropriate half planes into this torus, which have good asymptotics as, again, this should be an epsilon. I can never decide what this variable should be called, as epsilon goes to 0, and some kind of moderate growth as epsilon goes to infinity, and the correct jumping. So this now is an automorphism of the torus, so I can apply it to this element of the torus and get another element of the torus. And that's what we're looking for, okay? So it's a rather abstract seeming thing. And, you know, at this point, I'm basically going to go to some examples and try to show you how this can be solved.
Tom?
Yeah.
Can I ask a question?
Yes.
So solving the Riemann-Hilbert problem in diffeomorphisms of the torus seems already hard enough, but I assume it would be even harder if you did it in some appropriate whole algebra of the triangulated category.
Yes, I mean, I think so. I mean, so Valerio is talking about the fact that, I mean, there is something that lives above this Lie algebra of, or this group of, well, better to say the Lie algebra of vector fields on the torus. There's something that's defined purely in terms of the category called the Hall algebra. And the good thing about that is you don't need CY3. So that's a completely abstract thing, which works for any category. You can talk about wall crossing in that context. But on the other hand, this Hall algebra is a very abstract thing, which doesn't really connect with geometry in any way. Yes, I mean, I wouldn't really have, I think in general, it would be hard to solve it in that context. And then also it wouldn't be clear what to do with the solution, I suppose. Right, you would just end up with some holomorphic functions from stab into some abstract Lie algebra. I mean, of course, that could be interesting, but you wouldn't get the same kind of links with hyperKähler geometry.
Yeah, then you then have to map that into vector fields of the.
Oh, I mean, you're saying in the CY3 situation, maybe I should try and solve it in the whole algebra and then apply the map.
I'm sure you thought about that. So I was just wondering whether.
No, I mean, yes, I haven't thought about trying to solve them in the whole algebra. I mean, I think that's something Dominic is interested in doing in non-CY3 situations.
Okay.
Right. Okay, so that's the problem. So obviously it's too much to consider, but just try and process some of it. Of course, you're looking for functions. Basically, you're looking for a discontinuous function from C star into the torus, which is C star to the n, and it jumps in a particular way across rays. It has asymptotics of this form as it has moderate growth at infinity. It has asymptotic asymptotics of this form as epsilon goes to 0. And you know the constant, so the kind of exponential term in those asymptotics is the central charge, and the constant term is the thing you chose at the start here somehow. Because really this is tending to the identity as an automorphism of the torus, and when I apply that to this point, of course, I just get psi back. Okay, so that's the thing to think about. Right, and remember, I'm just sort of reminding you what we're trying to get out of this. We're trying to get this joist structure on the space of stability conditions, and which, you know, the main part of the data of that was some hyperKähler structure, complex hyperKähler structure on the tangent bundle. But really what it was about is a sort of pencil of nonlinear connections on this projection. Because as I explained, once you know how to lift vectors downstairs into tangent vectors upstairs in these two different ways, then you can just define the hyperKähler structure using, you know, you basically set the eigenspaces of the operator I to be this and this. Okay, so that's the sort of geometry we're supposed to be getting out of this. So the basic routine we're going to follow is we're going to start with the DT invariance and try and solve this problem, describing a function into the torus. So M is my space of stability conditions. So this Riemann-Hilbert problem depends on a point of that and a point of this torus, which is going to have these coordinates theta. And then we're going to substitute the components of this solution into the equation that we're taking the Stokes data off. So that, by this I mean that equation we had, you know, z over epsilon squared plus f over epsilon. You can basically just, you know, the solution to the Riemann-Hilbert problem is supposed to be a solution to a differential equation. If you plug that back in, then you will get this function w out, and then that's what's supposed to give you this Joyce function, Joyce structure. Oh, and then yeah, we'll also be interested in trying to describe the solutions using generating functions. And so there's probably a more kind of conceptual thing about what this DT, what this Riemann-Hilbert, what the solutions are. So I think, and I'll come back to this at the end if I have time, but hopefully I won't. The solutions to the problem, I mean, what are those in terms of the hyperKähler geometry? I think they're describing twistor lines in the twistor space of this hyperKähler manifold. Okay. So, yeah. And I mean, this is kind of obviously an inverse problem we're doing here. We're starting with the Stokes data and trying to get to the connection, right? So that's usually the hard way around. It's usually easier to start with the connection and compute its monodromy or its Stokes data, right? So, you know, perhaps an interesting question is, if you start with a Joyce structure, is there some way to define some associated DT invariants by looking at the twistor lines, looking at twistor lines with appropriate asymptotics and comparing them, you know, asymptotics in half planes and comparing them? I mean, is there some yeah, map the other way that's worth thinking about? And then, of course, this is a highly convoluted thing. Is there a more direct way to define this Joyce structure on the space of stability conditions? I mean, somehow, you know, obviously I don't know of one, otherwise I wouldn't be doing all this. You know, it's the obvious question. I mean, in some sense, it's clear that what I'm doing is slightly nuts. You know, I'm starting with DT invariants, thinking of them as Stokes data, and trying to solve this Riemann-Hilbert problem, which even in the finite dimensional setting is a subtle thing to get solutions to. So, okay. Right, so let's think about the simplest possible example. So this is, my category is going to be representations of the A1 quiver. So actually that's, well, the CY3 version of that. So my triangulated, in this example, my triangulated category contains a single spherical object. Okay, that generates it. So it's just got a single free sphere in it. However, to understand the Riemann, I mean, basically, if you just do that, then the Riemann-Hilbert problem becomes trivial. So you have to double, there's a bit of a trick with this example. You have to double the lattice. I mean, the essential reason for this is that the group of symplectomorphisms of the torus is abelian, and therefore you can't see it by getting it to act on, basically, if you try and get it to act on the torus, hang on, no, let me not even confuse myself by saying this. Basically, you have to double the lattice. So the Grothendieck group of the A1 quiver is just a single class gamma, but it's convenient. This is kind of a technical trick to introduce the dual of that thing as well, so that I get a non-degenerate lattice. And then I take the central charge. So to define this Riemann-Hilbert problem, I just need kind of the sort of DT data. So I need some lattice, I need a central charge, which I'm going to take like this, and I need to know what the BPS invariants are. And so there's just a single sphere of class gamma or minus gamma, so I get BPS invariants like this. Okay, so what do we expect then? So there are just two Stokes rays corresponding to the point Z and minus Z. This is where the BPS invariants are. And so if I take some non-Stokes ray, I'm supposed to be looking for some kind of map from this half plane into my torus, which will be C star squared. And basically this thing shouldn't change. I should just analytically continue it until I hit one of these red rays, and then it should jump. So if you think about for blue rays in this upper half plane, if I glue all the corresponding half planes together, I will get a well-defined holomorphic function in the whole of this green spotted area. Okay, just by sort of rotating this blue ray between this red ray and that ray. Okay, I will get this whole region here. And similarly, if I take a blue ray on the other side, I will get the kind of opposite region. So the slit will be down this side. And so I can compare those solutions in two, if I take the intersection of those two subsets of C, it's disconnected, right? There will be a bit here and there will be a bit there. So I can compare these solutions in two ways, and that will correspond to the jump across this ray and the jump across this ray. So my solution to the Riemann-Hilbert problem should consist of maps from this region into C star squared and from the opposite region into C star squared, which are related by the explicit birational map. And I should just say that this example is quite simple, and one of the ways to say why it's simple is it's what we call uncoupled, which means that if you take any two classes with non-zero BPS invariants, then their form is zero. Okay, this is trivially the case for this example. But in general, what that ensures is that the wall-crossing automorphisms for different rays commute, because this is basically the bracket in the Lie algebra. So anyway, so it means that, yeah, so the automorphisms for different rays commute. So if you want to solve the Riemann-Hilbert problem, you can just solve it for a single jump across one ray and then superimpose those solutions, one for each ray. And because the jumping commutes, that will work. Okay, so when you have an uncoupled example, you sort of expect to be able to solve this problem. Okay, so what is the DT Riemann-Hilbert problem? So for simplicity, I'm taking this theta equals 0, so this kind of constant term in the asymptotics. And so I'm looking for these two functions on these two regions that I just talked about. Yeah, so these are just the two components of this map into the torus. And here are the jumps. So the X guy doesn't jump at all, and the X hat guy jumps by the X. Okay, and these are these two regions to the right and to the left of that picture where the two domains overlap. So this is the jump across one of the rays, and this is the jump across the other one. And then there's the asymptotics. So, I'm just doing it component by component. So this is the central charge Z and Z hat.
Take there.
Say again. Sorry, Dominic, I didn't hear the question. I can't hear Dominic. I don't know whether anyone else can.
No, I couldn't hear him either.
Sorry, can I ask a question?
Yes, please do. Yeah.
Your equation, is it a bit mixed up? Do you want some x hat pluses there? And also, what is the x of epsilon the same as x plus or minus epsilon?
Yes. So right. Let me take those questions one by one. Is it mixed up? Quite possibly. Yes. Thank you. That should be a plus, and that should be a plus. Yeah, that's not very helpful. Yes, those two should be pluses. Apologies for that. And then your second question was clarification. Does this mean x plus or minus? Correct. So I don't need to write plus or minus here because this equation says they're the same. Yeah. So this guy is not jumping as I cross the line, so I can just put its value there.
Okay, thanks very much.
Thank you for that.
Tom, while we're on this, what is T?
Is epsilon. T is epsilon. I should have a vote for what's the best name for this variable. Sometimes I call it H bar, sometimes epsilon, sometimes T. But yeah, sorry for that. Thank you.
I like zeta, but just in your slide, you have x of epsilon and x of T in the last equation.
Yes. Yes, thank you. That's a typo. That should be an epsilon. I have some work to do on this slide, clearly. Okay. Right, so that's the problem. And the point is it has a unique solution. And so let's just, well, basically, X is not very hard to get because it doesn't jump, right? So it's just equal to its asymptotics. That's easy enough to see. The other guy is the gamma function, essentially. So here we go. So what to say about this? So it's not quite the gamma function. It's all this stuff is the kind of sporadic part of the Stirling expansion, right? So you just take that, exponentiate it, so you get something with a simple asymptotic series. Okay, and I mean, of course, this is kind of an undergraduate exercise to see why this is a solution to that problem I gave you, but let's just see the most basic thing. I'm claiming that the two plus or minus, the two solutions are sort of gamma of, essentially gamma of Z and gamma of minus Z inverse. So let's just go back to here, and you will see that since this is gamma of Z inverse, and this is, sorry, gamma of minus Z inverse, what this is saying is that gamma of Z times gamma of minus Z equals 1 minus, and this is just an e to the Z over epsilon. Okay, so it's basically the Euler relation for the gamma function with these extra factors in. So that's how you can solve that. And there is for simplicity, I assume theta equals 0. If theta is non-zero, you have to put, this one becomes e to the theta minus Z over epsilon. And here you have to put a plus theta, and everything is basically fine. You have to, it's a little bit more complicated, but one of the problems is that you have to, so I've been a bit coy about whether my solutions are holomorphic or not. So this solution is a holomorphic map from the required regions into C star squared. And that was certainly what I was hoping to find, but it turns out that when you put arbitrary theta here, you have to allow some poles in your solution. You can kind of see that that's going to happen just because the jumps have poles. So yeah, that's a sort of slightly unfortunate feature. But for theta equals 0, this is a unique holomorphic solution. And somewhat belatedly, I now realize that this is the classic, one of the classic examples in Resurgence. So if you look at an introductory paper on Resurgence, they will absolutely tell you about the gamma function. Well, the Stirling, I think they call it the Stirling function. And so in that vein, let's just look at the Laplace transform of this thing. So essentially the Borel sum of this series, then what you find is this function. So this is a function which has a pole at the integers essentially, and you take some stuff away so it doesn't have a pole at 0 anymore. So this is a function with a pole at all the non-zero integers, essentially, or non-zero multiples of Z, in fact. So that's what we were seeing in Marcos's talk as well, the idea that the Borel transform has poles at the central charges of stable objects. That's, or semi-stable objects, I should say. Okay, so that's the most basic example. So what's the associated Joyce structure? So I should say that to get the Joyce structure, you really do need to solve it for theta as well, because the Joyce function, or this Blavatsky function, is a function of z's and thetas. So the interesting thing is you substitute this rather complicated solution into the equation, which gives you W, and W turns out to be pretty simple. And in fact, the resulting hyperKähler structure is just flat. So it's almost that there's you've not gained anything at all. So the one thing you've gained is really that you already had a flat connection on stability space, which was the flat connection where Z and Z check. So the central charge coordinates are flat. Okay, and then we discussed this. Well, then there is also the Levi-Civita connection for your hyperKähler structure, and those things are different. And we discussed this linear Joyce connection, which is the Levi-Civita connection along the zero section. And in this flat case, that really is kind of everything. And so this connection differs from the kind of standard one. You know, the difference between those things you can write in this form for some function f on stability space, and it just takes this form half z squared log z. I mean, it's basically just, you get this connection by differentiating this thing 3 times, so you just get 1 over z, and then you sort of integrate it back up again. But I mean, this is a kind of a familiar form, I think, in physics for the pre-potential of something, for a very simple example.
What is that example, Tom?
In physics?
Yeah.
I mean, is it a U1 gauge theory? I don't know the answer to that question, I'm afraid. I mean,
Bobby, this is the leading term when you have a single electron. It's just, yes, it's like the conifold, yes, but I think in terms of field theory, it's to take the Seiberg-Witten for SU2, go to one of the monopole points.
Yeah, okay.
yeah.
You've got a light
Yeah.
charged hypermultiplet, charge 1. And so X is the X sub gamma coordinate for electric charge, and X hat is the one for magnetic charge. And you know this as the leading term in the pre-potential very well.
Yeah.
Mm-hmm. Thank you. It's very helpful for physicists to jump in and tell me what I'm doing. That's very useful. Thank you.
But I have to say, I don't know what the physics of the Joyce function is. And maybe somebody else on this in the audience does.
That might be
interpretation of that.
Well, yeah, I'll show you another one. So I'm going to go to the resolved conifold next. So maybe that will help. So I claim the resolved conifold is more complicated than this one. But first, so next there is this business about, so one should distinguish somehow between the Joyce structure, which, as you can see in this case, is very simple, right? I mean, here's the Joyce function. You get a flat metric. This is not a very complicated thing. But nonetheless, the solutions to the Riemann-Hilbert problem involved the gamma function and so on, right? So these were not trivial. And so that's something about, the difference between the hyperKähler structure and these particular twistor line, the equations for the twistor lines or something like this. So in this case, we want to write, it turns out, I want to write those solutions in terms of a generating function. So this was my solution to the Riemann-Hilbert problem. I take away the exponential part. So I get something very closely related. And then I write this equation. So I differentiate with respect to epsilon, and I think of a single function of z and epsilon satisfying this. So in other words, I mean, sort of the reason I'm doing this is that in general, there will be lots of central charge coordinates, and there will be lots of components of my Riemann-Hilbert solution, right? And so I want to encode them in a single function. So the way I do that is the ith component is going to be the differential with respect to zi somehow. Right, it's not clear that you can do this. I mean, this is just and this is something, so I should say first here that here I'm really just looking at the solutions for theta equals 0. That's somehow important. And as I say, it's not clear that you can do this. You can in the uncoupled case, but I suspect maybe that's the only time you can do it. But it leads to some interesting functions, which is why I'm doing it. So remember, maybe it's worth saying that this equation, this problem depends on a central charge and this theta in the tangent space. So it's the tangent bundle to the space of stability conditions which parameterizes these problems really. If you set theta equals 0, then you're just seeing some half-dimensional locus. Anyway, in this case, you can figure out what this tau thing is, and well, okay, it's not very different to the gamma function, obviously, because you've differentiated and you've integrated again. But what you get is this Barnes G function modified in the same way by taking away its kind of leading asymptotics. And so this thing has this expansion. So again, I don't know what the name for this is in physics, but I think this is a fairly familiar theory, a fairly familiar series. If anyone wants to enlighten me, then feel free. Okay, so now I'm going to move on to a slightly more complicated case. So, I mean, yeah, let's just do it. So this is the case of compact CY3, sorry, non-compact CY3 folds, which have no compact divisors. I think I can do it in that generality. But actually, I'm just going to focus on the resolved conifold. So that's the case where you just have, well, I think you know what the resolved conifold is, but it's it has a single rational curve in it with normal bundle -1, -1. And so the lattice that is basically the homology, is the cohomology of that P1. So to specify, you know, the Chern character of a compactly supported sheaf, coherent sheaf on this variety is given by two numbers that sort of rank in the degree on the P1. And the form is 0 because basically because everything is supported on curves. All compactly supported things are supported on curves, and two curves don't meet on a threefold, so the intersection form is 0. And you can actually compute the space of stability conditions in this example. So it's basically, you look at the central charge of, so this is an object, I mean, I should have written this differently. This is, yeah, I mean, think about OC of D. That would be the kind of classic object on the resolved conifold. It's a rank 1, it's a line bundle of degree D on the curve. So here I'm thinking about a rank R bundle of degree D on the P1, and this is its central charge, where V and W are these numbers which are parameterizing the space of stability conditions. And these things, these loci I have to take out because they would basically involve one of those branes having the central charge going to 0. Okay, so that's the space of stability conditions. So again, this is an uncoupled situation because of this. And again, you should double the lattice as we did before and consider this double thing. And then you get this diagram, which I've learned to call the Peacock diagram this week. I guess it's a peacock standing by a lake. And this is the diagram we showed before. So this is all the stable objects on this threefold. They're all the line bundles on the P1 sitting inside the resolved conifold, and all the skyscraper sheaves of points. Okay, and I shouldn't have really put these NXs because those are semi-stable rather than stable, but never mind. And these are the BPS invariants. All these guys are just kind of spherical objects, single spherical objects, so they all count 1, and then these move in a moduli space looking like, well, anyway, these contribute -2. Okay. So, you know, I would imagine that you're all groaning internally at the thought of trying to solve this Riemann-Hilbert problem. So this will now involve maps into sorted into C star to the 4, although as before, 2 of the components won't jump and will be just equal to their asymptotics. But the other 2 components will jump across each of these rays and also across this ray. So, you know, you can basically solve this by superimposing the gamma function solutions for all those rays and then trying to regularize what you've got. But anyway, you can solve this. And again, for theta equals 0, there's a unique solution. And, you know, if you're a fan of 19th century special functions, then you'll enjoy this exercise. So there is there is an explicit solution using things called Barnes double and triple, well, gamma functions. I should really say sine functions there. Those are related to the gamma functions. So there is some explicit solution. There's a paper on the archive you can look at if you care about. But let me just tell you what the output is. So again, this Joyce function, again, the metric is flat because it's uncoupled, basically. Because when these problems are uncoupled, you get rather trivial Joyce structures. And again, this is kind of a cubic in the fiber coordinates. Okay. So again, the only data really is this linear Joyce connection you're getting out. And this time, this pre-potential, so it's defined by a pre-potential in exactly the same way as the one before. And this time you get this thing, which is the genus 0 Gromov-Witten generating function. So, so indeed, you get a different set of flat coordinates on your space of stability conditions, and those flat coordinates are Kähler coordinates. They're or periods of the mirror. Okay, so you're getting some interesting data like this, and then you can also try to.
Tom, are you in the argument of the trilogarithm? It's exponential of v over w and not w over v. You're sure?
Here, yeah.
Yeah.
Yeah, it's v over w because tensoring by a line bundle replaces v by v plus w, because w is the 0 brane charge and v is the kind of 2 brane charge.
I see. So we could write it as w.
I mean, you should probably just take w equals 1. I think that's.
No, that. Okay. Okay. Yeah.
Yeah. I mean, this where was it? This central charge. I mean, I think.
No, I got it. Yeah.
Usually in physics literature, you would just take w equals 1. It's only because. Yeah. Anyway. Good. I hope you've seen it. So again, this job.
Can I ask you a question?
Yeah, please do.
Yeah. So I'm wondering, is there any role of theta in your geometry, in some Calabi geometry?
Is there any, sorry?
Sorry, role of parameter theta. So you consider the situation where theta equals 0.
Yes.
But what happens when theta is non-zero from some Calabi point of view?
From the point of view of the solution to the, so I mean, I didn't tell you the solution anyway. So the general rule with these things is that you, I mean, usually you have a lot of z over epsilon, because z over epsilon sort of goes together because that's the asymptotic, and you just change the z over epsilon to z over epsilon plus theta. And then you have to sort of play around with the special bits. So that's the rule here. So so here, if you wanted to introduce, sorry, where is it? If you wanted to introduce theta into this one, yes. Yeah, here you just put z over epsilon plus theta, but then here you have to do sometimes you put theta and sometimes you don't, and it's a little bit tricky and you have to figure it out.
Yes, yeah, I understand what happens for the solution when theta is non-zero, but is there any role of the parameter theta in geometry?
Oh, no, I don't. Yeah, that's a reasonable question, because no, I don't. Yeah, I don't know the answer to that. Sorry.
Okay, thanks.
So where were we? Okay, so as before, so the actual Joyce structure is not so complicated, but of course the solutions were quite complicated, and we can write them in terms of this a function tau in just the same way as we did before. And the interesting thing here is that we get the higher genus invariants coming in here. So I didn't write down, you can find them in the paper, what happens for genus 0 and 1, but this tau function has an asymptotic expansion, which just gives you the higher genus Gromov-Witten invariance of this resolved conifold. So I guess this is the curve county bits, and this is the zero branes, constant map contributions. And you see, you're not just getting this generating series, you're getting a particular function which has this as an asymptotic expansion. So you could, if you wanted to write a grant application, you could call this a non-perturbative partition function, right? Because it's a genuine function whose asymptotic expansion is the usual partition function considered as a formal series in the string coupling. So epsilon here is playing the role of the string coupling, basically. So this is the function, and then you have to mess with it a little bit just in the low genus terms. Yeah. So, I mean, this tau has a particular definition. There was a unique solution to the Riemann-Hilbert problem. So tau is a uniquely defined function, and it's not quite this h. You have to modify it in genus 0, well, by this bit. But basically, it's this quite simple contour integral. So again, this is some sort of Barnes triple sine function.
Is the Riemann-Hilbert problem solution unique for all theta, or just when theta equals 0?
Just for when theta equals 0. When the trouble is when theta is non-zero, you have to allow poles in your solution. And if you just say, okay, I'll just ask for any old meromorphic solution, then of course you can multiply it by all sorts of crazy, you wouldn't affect the jumping if you just multiply everything by some meromorphic function on C. Okay, so that will give you some awful amount of non-uniqueness, which is a problem. However, there are obvious places where you should allow poles, and if you try and say that the poles are only allowed there, then you don't get much non-uniqueness. So, it's not quite as bad as it sounds, and it's kind of obvious what the correct solution is. But no, I don't have uniqueness results in general. Okay, so and I just want to throw this out there as a kind of point that the joist structure was basically encoding the genus 0 data. Somehow this the solution to the Riemann-Hilbert problem is seeing higher genus data. And on the other hand, I mean, if we believe this statement, which I haven't really got to, which about the solution to the Riemann-Hilbert problem being sort of describing twistor lines for this HyperKähler manifold, then you could say that this is some implicit way of getting from the genus 0 data to the higher genus data. I don't know whether that's a reasonable thing to say, but I mean, it smells a bit like that. Okay. So those are the ones that I know that you can sort of get your hands on explicitly. Let's just think about these quadratic differential examples and how those might work. And this is really following Gauto, Moore, and Knightsky quite closely. So we take this category D, which was some Fakai category of symplectic threefold fibered over a Riemann surface. And this was the class of examples that Ivan told us about, where the space of stability conditions modulo autoequivalences is this space of quadratic differentials. And then we had this diagram that I was telling you about last time. Don't worry, this won't last for very long. So let's just explain this once more. So M is parameterizing Riemann surfaces with a quadratic differential. And we're interested in the tangent bundle, the total space of the tangent bundle, or rather a C star to the n bundle over that space. And the tangent space of this thing is H1 of the spectral curve. So what we want to do here is parameterize elements of H1 of the spectral curve with C star coefficients. And so that means I should take a line bundle on the spectral curve and an abelian connection on it, because the monodromy of this pair will be H1, live in H1 with C star coefficients. And then I explained that this data is, at least birationally, equivalent to some different data, namely a bundle, a rank 2 bundle downstairs with a connection and a Higgs field. So most of this is quite standard. The fact that you can push forward the line bundle and get a vector bundle, and then because this was on the spectral curve, you will get a Higgs field automatically. What was non-trivial is that this connection somehow corresponds to this one. And then we can consider the monodromy of this family of connections, nabla plus epsilon inverse phi. And then a further step. So this monodromy map lands up in some sort of, in the character variety. It's not quite the standard character variety because of these poles. And in fact, this is the variety that Fock and Goncharov defined their coordinate systems on, their birational coordinate systems. So putting this all together, for each point in M, you get a map from C star to the N, this fiber, to C star to the N. And that's depending on epsilon. And that's your solution to the Riemann-Hilbert problem. So it's a bit of a complicated story. And the point is that, yeah, so okay, so let's just think about some of the properties of this. So as epsilon goes to infinity, this term just goes away, and we just talk about the monodromy of this connection. Well, okay, we should just get some finite thing there. So that should be no problem as epsilon goes to infinity. As epsilon goes to 0, the monodromy of a connection like that, that's the, WKB analysis tells you about that. And, people who know about that will know that these Goncharov coordinates behave in the way that you would want as a solution to the Riemann-Hilbert problem. And then how do you get the jumps? Well, the jumps correspond to changing this triangulation. So the whole point about the Fock-Goncharov, one of the features of the Fock-Goncharov coordinate systems was that as you check, they depend on a triangulation of your surface S with vertices at the poles of your differential. And as you change this triangulation, if you do a flip, then you get a birational map of C star to the N, exactly of the form appearing in the DT theory. Okay, so that's this complicated thing. The vast majority of this is Gayato, Moore, and Knightsky's beautiful ideas. This part of the story, the Fock-Goncharov things, is exactly as in their paper. The WKB analysis, as epsilon goes to 0, is exactly as in their paper. So, most of this is really just their work. But, as I said before, this is a little bit different. So I don't really know how to prove this completely yet, but the claim is that, so if you have this quadratic differential Q, then its horizontal foliation structure determines a triangulation. Ivan drew that for us. So you actually do it for epsilon inverse Q. And so you should take T to be that triangulation. And then as epsilon crosses certain rays, this triangulation will flip, and that means your coordinate system will change by some birational map, and that will be giving you the discontinuities in your in your Riemann-Hilbert problem. Okay, so as I said, this is very closely related to work of GMN from 10 years ago. The jumping is given by the properties of the Fock-Goncharov coordinates. You need the WKB analysis to check the behavior as epsilon goes to 0. And Dylan Allegretti has given proofs of this conjecture that, that the Riemann-Hilbert, this gives solutions to the Riemann-Hilbert problem in the cases that theta equals 0, which actually corresponds to the connection nabla being an opper. And together with Davide Massoero, I completely checked this in the A2 case. So in the case where Ivan also explained that example. So it's the simplest example of this story, and you can really prove that you get a solution to the DT Riemann-Hilbert problem, and it leads to that Joyce structure that I discussed a bit yesterday. And that, at last, is not flat. That's a non-trivial Joyce structure. I wrote down the Joyce function for you in lecture 2. So that's my first non-trivial example, but I'm hoping that there will be some more here by just pinching the ideas of GMN, of course. So I think I'll make this my last slide. So let me discuss just some links with others' work and some further problems. So the thing that I would most like to understand is this business about generating functions. So I defined that sort of tau function earlier. It gave nice answers in those uncoupled cases. I mean, it gave this Gromov-Witten generating function for the resolved conifold. But I'm not sure that definition makes sense in general. And, you know, so I really want to understand how to write down the correct generating functions. And here are some clues. So if I take the 0 section in this example I've just been discussing, so remember the tau function was about looking at the theta equals 0. And then the solution in this example I've just discussed would be giving the Fock-Goncharov coordinates of the monodromy of operas. So there's this famous work of Nekrasov, Rosalie, Shatisvili describing the generating function for the Opper locus in terms of things interesting in, well, in physics, in what are they, quantum integrable systems. So there is a, you know, there is a nice generating function here, and maybe that's one of the things one should put into this. On the other hand, if you ask for the solutions to that Riemann-Hilbert problem I've just been discussing to be constant, what you're asking for is that this family of connections is isomonodromic, right? Because the solutions were just describing the monodromy of those connections. And that gives you a relation to Pan-Lavey tau functions and isomonodromy tau functions, which in turn, by work of Koman, Longy, Pomoni, and Teschner, these are related to the Gromov-Witten generating function of the mirror of the threefold that we took the Fukaya category of. So let me just take a step back a minute. This last class of examples I was discussing, I got them by taking the Fukaya category of some CY threefold fibered over a Riemann surface. That CY threefold has a mirror, and it's the Gromov-Witten generating function of that mirror threefold that that gets related to this isomonodromy tau function. Of course, that's perfectly appropriate because I've switched sides of the mirror, right? So my first example when I was talking about the resolved conifold was the B model. I was taking the derived category of coherent sheaves, whereas in this case, I'm taking some Fukaya category. So, you know, it's sort of consistent. And then there's also work of Kohei Iwaki and Kidwai, where relating this this tau function that I defined earlier to the partition function computed by topological recursion. So this is for some pretty restricted class of examples, some class of spectral curves corresponding to hypergeometric functions. So these are uncoupled cases, so this tau function makes sense, and they showed that it matches with the thing computed by topological recursion. But that, again, is some kind of intriguing link. And so, so yeah, this is the thing I think I would most like to understand at this point. And then another further direction, but I think this is, I'm not sure I have the energy for this just now, but maybe other people do, which is that there is a refinement of this whole story where instead of ordinary DT invariants, you use refined DT invariants. So they've got Q's in them. You know, instead of Euler characteristics of moduli spaces, you're taking Poincare polynomials, essentially. And so you get something, instead of automorphisms of a torus, you should think of automorphisms of the quantum torus. So that's some non-commutative algebra. And we thought about the A1 case in much, you know, with Anna Barbieri and Jacopo Stopper. So that's there you get, instead of the ordinary gamma function, you get the double gamma function. So there is some, you know, we did some work on this, but it's, you know, it's a very simple case, and it already was quite a headache. I suspect that if you were good enough with special functions and patient enough, you could do the resolved conifold case in this setting as well. And presumably get the fully refined topological partition function for the resolved conifold. But it will be really, I mean, interesting to understand this class of examples relating to quadratic differentials in this refined setting. And that would presumably use this realization using skein algebras of Fei-Yan and Andy Knightsky. Okay, so there's just some connections with other people's work. I'm sorry for going over time. I'll stop there. Thank you.
Thank you. Thank you, Tom. So, do we have questions?
Yeah, I have a question. Thanks, Tom, for the wonderful lectures. I was curious about this uniqueness issue. So to what extent are the DT invariants somehow encoded in the connection that you get up to gauge equivalence? And so then can you use some more invariant construction of the connection, like you're proposing here, to extract the DT invariants?
I mean, this is kind of a sort of a backwards construction. So once you carry it out, it's easy to go back to the DT invariance somehow. So when one constructs a joy structure in this way, although you'll see that most of the joy structures I constructed were pretty simple, but nonetheless, you can then prove that this kind of associated differential equation has nice solutions with good asymptotics in half planes, and that they then differ by the DT invariance somehow, right? Because that's how you constructed the thing.
Right. So I guess the idea would be like if you had some a priori other construction of this connection, then you could read off the DT invariance from the connection by looking at solutions. So is there any chance of constructing that connection by categorifying everything and like using this whole mixed Hodge formalism?
I
Maybe
mean, that
expressing it as a Gauss-Manin connection or something like that.
Yeah, no, I have no idea about how one would do that. No, I mean, so yeah, I mean, it's sort of, I mean, in these examples of joy structures, someone gives you one of these things and it tells you just the joy structure is given by this function theta cubed over z. It seems a ridiculously simple thing, but then if they ask you to construct solutions to the connection with good asymptotics in half planes, then somehow you would have to realize that you had to write down the gamma function. And then you can compare the gamma function and gamma of minus, and you would work out the DT invariance of that joy structure somehow. And yeah, I mean, but I don't know from the point of view of category theory, just starting from this CY3 triangulated category, I have no idea how to get the joy structure without going through all these loops. But at least now we know what we're looking for, right? So, the only way this is going to really turn into respectable maths is if we come up with some other construction of the joy structure, and then it becomes a theorem that, this joy structure has nice solutions in half planes, and the DT invariants are what controls the overlaps. And maybe there could be some way of doing that if you assume your category is geometric. If it's a Fourier category of some sort, maybe someone can come up with a good construction using geometry. But I find it hard to imagine at the minute a construction that just works at the level of triangulated categories of this structure.
Okay, thanks.
Thanks.
Can I ask, I was interested in the GMN TT star geometry thing and what you said, and the conformal limit. And is a conformal limit simply some kind of limit which turns their equation into your equation, or what?
Yes, I mean, I think so. I think, if we go right back to this equation, Where was it? Yeah, so if we look at this equation, then you know, if you just rescale u and epsilon at the same time, send them both to 0. I mean, you should put epsilon on here on this side, right? So then you've got u over epsilon plus v plus epsilon u bar. And then you send u and epsilon both to 0, keeping their ratio somehow constant. Then this term just goes away. And I think that's the analog of the conformal limit somehow. Yeah, I mean, this equation has some homogeneity, right? If you rescale u and epsilon simultaneously, which this one doesn't. And somehow you know, by taking the conformal limit, you get to this kind of homogeneous situation, something like that.
Sorry, if I may ask here at this point, because I mean, my understanding of the conformal limit was that this is the limit which goes from the non-holomorphic flatness conditions in the Hitchin system to the purely holomorphic differential equation. So on the level of the holomorphic differential equation, it wouldn't do anything.
That's right. That should be good. Yeah, because I mean, again, if I rescale u and epsilon here, it shouldn't do anything.
Yeah, right. So we are already in the conformal limit here. So
absolutely, my whole story is happening in the conformal limit. This is not in the conformal limit. Yeah, and you know, this is analogous to that thing you would see in the Hitchin system of kind of phi over zeta plus a plus phi bar zeta. Right?
Yeah, but one would also have sort of another equation where no, sorry.
I mean, it's a shame I didn't put the epsilon over here.
Okay. Any more questions?
Okay, so
sorry, I had.
Yeah.
So if I could, I wanted to ask a little more about the isomonodromy condition that you mentioned at the end. Sorry, I'm trying to find it again. So you said that oh goodness, sorry. Yeah. Okay, so you said that something gives you an isomonodromy condition for these connections, delta plus
V
over epsilon. So if I understand right, you're saying that like there's some condition which says that as you move around this abelianized connection in X, those, I guess I would think of them as like Schrodinger equations if you're in SL2. Like those Schrodinger operators end up having constant monodromy.
That's right.
Yeah. Sorry, go on.
So yeah, I mean, it would be something. I mean, after all, this is the monodromy. So if I want to, so my solutions are given in terms of the monodromy of this connection. I mean, they're the Fock-Goncharov coordinates of this connection.
Right.
So asking for those to be constant is asking for this connection to have constant monodromy. So at least part of this story is varying your Riemann surface and asking that your connection has constant monodromy.
I understand. Okay. So, wait. I guess I'm confused because I usually think of like a topological setting where the data in X, I mean, okay, let me say it another way. I had thought that the data in X was just, so it's a surface, topological surface. It's a line bundle and a connection on the line bundle. That's like a purely topological thing. And to me, it seems like if you change it at all, the monodromies necessarily change. And I don't see sort of where how the complex structure appears at all in the left. So where is,
so I mean, S here is a Riemann surface, right? So I'm parameterizing pairs of a Riemann surface and a quadratic differential.
Okay.
And this is a holomorphic line bundle and a holomorphic connection on it.
I see.
On the cover.
Okay.
And so what you're getting is a sort of I mean, it's better seeing it at this level, really, which is saying that as I vary my Riemann surface and I mean, basically, as I vary my Riemann surface, how can I vary my connection and a vector bundle so that the monodromy is constant?
Yeah.
I mean, it contains that system within it, but this is, as usual, we've sort of doubled the dimension, so we've got this extra stuff going around. So it's not quite exactly that, but it seems related.
Is the isomonodromy condition just equivalent to asking for movement, like motions within X, for which the holonomies of delta ab remain constant?
No, because the holonomies of delta ab is the theta coordinates. So in other words, if you think about the components of this map, if you call those xi's, then asymptotically the xi's are zi over epsilon plus theta I, where theta I is the holonomy of these guys.
Oh, sorry. Okay. So okay.
Okay. Can I break in?
Yeah.
Perhaps we could call an end to the main session at this point, so that people can have a break before Simon's talk, which is in 15 minutes. Maybe if a few people want to stay and chat